So, welcome back from the break. Welcome to Hoon Academy Lesson 5. So, this is a pretty important lesson today. We are going to begin learning about the pattern called cores. Cores are really the last remaining major concept in learning Hoon. Once you understand them, you're on your way to having a good understanding of the whole language. Basically, every working piece of Hoon code you're going to encounter, from big to small, is a core. So that's why understanding them is very important. So let's get started. What exactly are cores? Cores are simply a pattern for storing code as data. So what do we mean by this? Um, let's go back to the early lectures. Remember that Hoon compiles to knock. Hoon is knock underneath. And everything in knock is just a tree of natural numbers. So in particular, if you remember when we did knock subject formula reductions, we had the subject, which was a tree of numbers. That was the data input that you're working with. And you also had a formula, which were instructions. That was also a tree of numbers. So they look very similar. And in fact, they have the same representation. Both code and data have the same representation in knock. When code and data have the same representation, that's a term called homoiconicity in programming language. If you have background in other languages, you may have heard of that, but no worries if you haven't. But that's just what it's called. Okay. So with this equivalence, it would be nice to store a tree of instructions at some location and be like, hey, this is not just data, but this is actually computational instructions at this location that I can pull out and I can run later. And this is exactly what cores let you do. Okay. So a core is simply a pattern for storing code as data and data as data in a binary tree. And the layout is very simple. So the code stored as data goes on the left, and the data stored as data goes on the right side of the tree. In Urbit terminology, the left branch of the core containing the code is called the battery, and the right branch is called the payload, which contains the data. So more concretely, the core is going to store code in several addresses in this left side, in this battery, in locations that are going to be called arms. And then whenever you build a core, remember that every piece of Hoon code has a subject, its data environment that you're building against. It's going to take that subject and put it in this right side in the payload, okay? So before we start making and using some cores, let's recall a few runes. Remember that we learned this Tisgar rune, which takes two children. It says, here's my subject, here's my data environment that I'm going to use, and then here's some formula that I'm going to evaluate against it. Here's something I'm going to do with the data environment, okay? So we used this rune before. Hopefully we remember that. And we should also remember the Tisgal rune, which is exactly the same, but the argument's inverted, Tisgal, just like that. Right. Okay. So let's see our first core. So considering this following code right here, okay? And I will paste it in chat for you guys. Okay. So this piece of code. So what's going on here? Let's introduce all these new parts. So we're learning a new rune here called bar sen. And bar sen is the general rune to make a core. Okay. So what are you going to do? You're going to start off with a bar sen. You're going to have the lust, which designates a particular arm that you're creating. Then you're going to give that a name, and then you're going to put some Hoon code to store inside the arm. And then you can do that as many times as you like, and you close it with this hep hep at the end, okay? So that's what we're doing here. We're ~send, making a new core, making an arm called increment 100. Here's the code we're putting in it, and then we're closing it off, okay? Here's the all the explanations of these parts right here, okay? So when we took this code and we ran it, we got an output that looked like this right here, okay? That was the output from running our code. So what does that mean? This returned a cell. The head of the cell is this 1.oks, and that is a summarized statement indicating that there's one arm in the core, and that's our one arm that we defined right here, okay? And then this right here is the tail of the output, okay? The tail of the cell. Let's recall that every statement, every piece of code that we type in the dojo is implicitly dojo subject as a subject, right? So in fact, what happened here is this core took the entire dojo subject and it put this summarized version right here in the tail of the output, okay? And all these lines here are describing the dojo subject. It's saying there's a core with 15 arms, there's a core with 40 arms, there's a core with 14 arms, and so on and so forth. Okay, so that's what happened when we ran this code. This is the output of the core. It's in a pretty printed summarized version because it would be a pretty big, if you actually wanted to print the entire dojo subject, that would be a pretty big piece of data to output, okay? Okay. So let's prove that this is indeed the dojo subject right here. So what can we do? We can pin something to the head of the subject right before running this code, and then we can see that it will show up inside of this output of the core, okay? So recall that the tis less rune pins something to the head of the subject, and then it computes the rest of the hoon in that new subject, okay? So here we're just saying let's pin num1 equals 1 to the head, and then let's create our core. And then what happens? Let's examine the output right here on the second line. In the head of the tail of the output, it says num1 equals patUD. And that was not there before. Now it's here. And that's because we put this at the beginning of our subject before creating the core. Okay. And we can do the same thing with the tisfaz rune. This does the exact same thing structure-wise. It's just separating out that name. So we can do num2 equals 2, and then create our core, and then we get that num2 that shows up here, right? And this diagram here is just showing you where in the data structure that newly pinned number is going. So as we recall, the data is going in the right-hand side of the core, and then this is going in the head of that, okay? And also recall that the specific dojo syntax like this, you can also pin something to the head of the dojo state a bit more permanently. That will also make something show up. We pin num3 to the head of the dojo subject right here, and it showed up right here in the core, okay? So now let's remember the tisgar rune again. What happens if we do this? Let's set the subject to just the null value, just sig, and then let's create our core, okay? Now that's kind of interesting. So basically, we said, let's build our core against a subject, which is just sig. And what happened is that sig is now in the right-hand side of the core. You can see this output is much shorter now. It just says you have one arm, and then you have a payload, a right-hand side, that is just sig, okay? All right, so any questions on that? You should understand why this piece of code produced this output, okay? Okay, so we've looked a little bit modifying this right-hand side of the core, modifying the payload, the data side of the core, right? So we're changing the subject, and then we're building the core, and then we're getting a different output here, right? Let's look a little bit at this left-hand side of the core, where the arms are stored, where the code is stored, okay? So arms in a core are stored as uncomputed knock. They're not evaluated yet. So let's prove this. Let's make a core and let's pull out what's in one of the arms, okay? So if we recall our tree addressing, if the whole core lives at the +1 address, then the arms, being the left-hand branch of the binary tree, should live at the +2 address. And the subject the core was built against should live at the +3 address, okay? So let's take our increment 100 core again, and then let's grab its +2 address. Let's see what's in there, okay? And what's gonna happen? So it's gonna give us this cell 41100. What does that mean? So I'm gonna claim that this is the raw knock that says take the number 100 and increment it by 1. So exactly what this piece of code does in knock, okay? So let's confirm that. How do we reduce this? How do we interpret this piece of knock code? Knock 4 says to increment the result of running whatever's after it, okay? So if we pull out that knock 4, we're going to say compute 1/100 and then increment the result of that. Now, knock 1, what does knock 1/100 do? Knock 1 says, forget about the subject, just throw it away, we don't care about that, and just return what comes after it, okay? So we're just going to return 100, and then we're going to increment 100 to get 101. So that confirms that this 41100 is indeed the knock code to take the number 100 and bump it up by 1, okay? And we can also check this with a .tar room, which runs a piece of knock. So since our subject doesn't matter here, we can just give it sig as a subject. And then we're going to type the knock 41100 and see what that does. See? And that'll give us 101. Okay. So just to recap, what do we do? We took this core. We built it, we set it as a subject, and then we grabbed its +2 address. Oops. Sorry. We built this core, we grabbed its +2 address where the arms live, and then we saw that this knock code popped out. We ran that knock code and we confirmed that it is indeed the code to increment the number 100, okay? However, let's compare that to a different way of storing 100 plus 1. So recall that the TISFAS rune pins something to the head of the subject. Let's make that to be increment 100, okay? So let's say we're basically declaring a new variable called increment 100, and we're going to say, well, that is the result of taking 100 and incrementing it. Now, if we return it, increment 100, we get the number 101. So there's a difference here. Um, these arms in a core are stored uncomputed and are computed when you call them. While when you pin something with this TISFAS, you compute the result and then you stick it in the subject. Okay. And if you're familiar with some other languages, you might conceptualize this as lazy evaluation. The arms in a core are evaluated lazily, and eager evaluation, which is right here. You're eagerly evaluating that result and storing it. Okay. Any questions on that? Okay, so we've dissected the structure of this basic core a little bit. Let's actually try to use cores. Okay, so running an arm from a core is pretty simple. Um, if the core is in the subject, you can just call the arm by its name. So let's build this core, put it in the subject, okay? And then we're just going to call one of its arms increment 100. And that gives us 101. Okay. Um, if you want to like give this core a name with this TISFAS, let's build this core, let's call it my core. Can I still call that arm increment 100? Um, Unfortunately, I can't. If I do this, if I give it a name with this TISFAS, then I actually have to do I have to do this increment 100 dot my core. So since this has a name, my core, you have to say, let's look inside my core and see there's an increment 100 in there. Okay. That gets you the 101. Um, okay. So these arms inside the core can refer to objects in the payload, can refer to objects in the data, the right-hand branch of the core. Okay. So let's consider this piece of code right here. So we're pinning n equals 5 to the head of the subject. Then we are defining this core with a single arm increment n. Increment n is going to look for something called n and then return it with a +1. Okay. So if we call that arm, it's going to find that n equals 5. It's going to return 6. Okay. And hopefully it's clear from this example that if we change that n to a different value, and then we call increment n, it's going to grab that different value and increment. Okay. Um, so again, we're attaching this new value to the subject that's getting stored in the data side of this core, and then inside that core, it has an arm that's grabbing that data and acting on it. Okay. Any questions on that? So here we see the different parts that are going on. This TISLess n equals 5, that's adding something to this right branch data side of the core. This arm increment n, the single arm in the left side of the core. And then our formula we'll be doing with this, what we're calling that arm. Okay. So as we mentioned earlier, this left branch of the core, which contains code, is called the battery. And this right branch of the core, which contains data, is called the payload. Okay. It's a very common pattern to do what we just did, which is pin something to the head of the subject, top of the subject, before making a core. And this makes up that thing show up at the top of the payload. Okay. Um, when that happens, we say the payload is a pair of sample and context. And sample is a thing we just added, and the context is the rest of the data context, that the rest of the subject that you built the core in. Okay. We can map these three terms back to our example. In this case, the battery, the arm of the core, the single piece of code in the core was just as increment n right here. The sample was this n equals 5 that we put in the head of the subject. And then the context is the rest of the subject that the core was built against. In this case, that would just be the rest of the Dojo subject. So all those standard library functions and all that are going to be wrapped up and put in here. Okay. Okay. So let's slightly increase the complexity of the cores that we are able to use. We've been looking at cores with just a single arm, but obviously they don't necessarily have to have just a single arm. So here we're making a core with 4 arms. We call the arm FOUR, and it returns the number 4 because that's what's stored in there. Okay. Arms and cores can refer to each other. So here in this code, the arm 1 just returns a number 1. The arm 2 returns the result of incrementing the result of calling the arm 1. The arm 3 returns the result of incrementing the result of calling the arm 2, and so on for the arm 4. Okay, so this one refers to this one refers to this one refers to this one. Okay. So if we run this code, the calling the arm 4 returns number 4. Okay. Something else we can do with cores is we can store type definitions inside of these arms. Okay. If we use this arm rune less buck instead of less, what this does is it switches this into structure mode instead of value mode. So this lets you put type definitions inside of cores. Okay. If you recall that in lesson 3, we were making custom type definitions like reptile and reptile tracker. You can now store these inside of cores, which you can then pull out and use later. Okay. So, for example, we can make this core with our types reptile, which is either a send snake, send lizard, or a send crocodile, and our type reptile tracker, which indicates a species and how many meals it's eaten, right? Remember we did that before? And then we can use that type stored in the core to do a type cast. Okay. Okay. So any questions on that? So let's take a moment to make sure we understand what's going on. We'll need to do a little bit of mental shape rotation. Okay. So when we use this bar send rune, we are storing a copy of the subject at the time that rune was executed. Okay. So there's some subject that you built this core against. It's going to grab that and it's going to put that in its right arm, okay, in this right branch, and then in the left hand side, it's going to have those arms, right, those pieces of code. Now, if you set the core then as the subject. So if you're going to make a core and then you're going to set that core as the subject for the execution of some code, That means that you kind of have like a subject within a subject in the sense that this new subject is the core. And in that right-hand side of the core, it has the old subject, which is the subject the core was built against, right? So this core kind of grabs this data environment, it puts it inside of it, and then that whole thing becomes this new data subject, okay? If I instead use tisfas to like give some name to this core that I want to refer to, okay? So again, you're making the core. It's going to grab the data environment that it's built against and kind of like wrap around it, right? But then you're saying, let's take that structure that we created and let's put it as the head here. Then in the tail of the subject, um, that old subject is still there. So there's you kind of make two copies of the same thing. One which lives inside of the core and one which is in the right branch of the original subject. That happens when you use this tisfas rune to declare a new core. Okay. Um, Fortunately, when this occurs, you don't actually duplicate the whole structure. Memory management prevents, basically makes it so that if you duplicate something, you're just referring to that same location in memory. So this doesn't use twice the memory, but it's just uh, important to note that if you do this, you're kind of making two copies of the subject. Good. Okay. So if we understand kind of these two graphics here, then we are ready to start composing cores with each other. And this is important because every piece of Hoon code basically is cores composed with each other. And so if you can kind of understand this, you can understand the structure of basically every Hoon program you're going to come across. Okay. So let's look at this piece of code right here. Okay. I'll put that in the chat. So we can parse this code in the following way. Okay. So at the top, there's a tisgar. We're setting this core as a subject for the evaluation of this. Okay. Make this core set as a subject, then evaluate this. What is this? Well, it says make this core as set as a subject and evaluate this. Okay. Um, those two operations are going to create a data structure that looks like this. Okay. We have a core on the outside, and it has an arm, this outer core arm. And on the inside of it, it's going to have an inner core stored in its data side, right? This inner core has a single arm, and then on the right-hand side of that, it's going to have the entire Dojo subject that you built this against. Okay. And again, the data structure came out this way because you made this against the Dojo subject. You grabbed the Dojo subject, put it in its right-hand side, and then you made this thing against this thing. So this thing grabs this thing and puts it in its right-hand side. So hopefully that makes sense about why this piece of code creates a data structure that looks like this. Okay. And if we run this code, oops, run this code, it's going to pull that inner core arm and return that text. Okay. Okay. When you pull and run an arm and a core, it's going to use its parent core as a subject. Okay. So if I run this inner core arm, and which returns n, it's going to look in this local scope for something that's named n and return that. Okay. So this piece of code is very similar to the piece of code we just looked at, and it's going to produce a data structure that looks like this. Okay. So you have an outer core, has two arms, an inner core, which has two arms, and then the dojo subject that you built this whole thing against going on here. Okay. So if we take this code and we call this inner core arm, which looks for something called n, it's going to return the number 2 because it's going to go in here, be like, okay, I found an n. It's this other arm. It returns value 2, and that's what you get. Okay. Now, even if you add this piece of code right here, pinning the value n to 10 before calling this inner arm, even though it looks like that maybe we're defining n to be 10 before you invoke n, this ends up all the way out here on the outside of this data structure. And the scope of this is only in here. So it's not going to pull that n equals 10. It's still going to pull n equals 2. Okay. So this still returns n2 when you call this on. Now let's move this n equals 10 around a little bit. If we move it all the way up here, that makes it part of the subject at the time that the inner core is defined. That means that this n equals 10 is going to be the head of the payload, the head of the data branch of the core. Okay, so this n equals 10 is going to end up inside of this inner core, but it's going to end up on the left-hand side of this right branch right here. Okay. If we run this code, that's still going to return n equals 2 because it's going to search for something called n, and it's going to search this left-hand side. It's doing a depth first search. It's going to search here first, find this arm n, and not find this. It'll find this second. Okay. Now, if we modify this code, okay, so if we take this piece of code and remove that arm n from the inner core, okay, we remove this arm here, and it's gone here. Now, by calling this arm, which looks for something called n, it is going to find this first, okay, and we'll get 10 this time. And then if we take that n equals 10 and move it back to the outside, if we move it back to the original position, then it's not going to find n because the n arm is gone, then it can't even find these n's that are outside. Okay. Does that make sense, everybody? Are there any questions on that? Okay. So moving on, we can keep composing cores and nest them within each other as deep as we want. Okay. So consider this piece of code right here. We're nesting this core within this one, and then we're nesting this core within this one, and then we're going to look for something called buck. Okay. Usually when a core just has one arm, we give it a default name of buck. So that's why these are all just have one arm. They're called buck, and then we're going to look for that. Okay. So In the outermost core, there's a single arm buck, which returns 1. In this inner core, there's a single arm buck that returns 2. And in this most inner core, there's a single arm buck that returns 3. Okay. When we then invoke buck, we do a depth first search. So we're going to go in the left-hand side, search as deeply as we can, and then we hit this buck 1. Okay, that's why we return 1 here. If we want to find the next one, you can use the syntax that we learned before, which is recall that this ket means skip the first match and get me the second match when doing your depth first search. That will then skip this one and return the number 2. Okay. And if we want to do skip the first 2 matches and get the third match, then we can just do ket. Okay, and that'll get us the number 3. So because of the way these nested cores are laid out, it searches all the arms of the cores. You're going to search here, search here, search here before searching the rest of the data that you have. Okay. Any questions on this? So besides composing cores with this tisgar, there's another way to nest cores inside of each other. Okay. So far we've been putting cores inside of the right branch, the data branch of other cores. You can also put cores inside of the left branch of another core, inside of the code branch, inside of the arms. Okay. Let's see an example of that. So this piece of code, so what are we doing here? We have a core with a single arm that's called core in arm. That arm contains a core which has a single inner arm, and that returns some text. Okay. So you have an outside core, and that core contains another core inside of one of its arms. Okay. If we try to invoke inner arm, we will get an error, find.innerArm. Why is that? Well, that's because this core isn't built yet. Recall that this code inside of arms is lazily evaluated. It's not, this is just raw knock that exists here. So the Hoon doesn't know about anything called inner arm until you pull out and evaluate this thing. Okay. So how can we actually create this so that we can actually invoke this inner arm here? Here are some ways you can do that. These 3 syntaxes are exactly equivalent. Okay, so what we can do, we can set this thing, and then we can then set core and arm as a subject. We're pulling out this thing and building it. We're setting it as a subject for the evaluation of something else. And then we're doing inner arm. And that's going to work, and that's going to return this text for you. Okay. You can do the same thing with the arguments reversed with this tisgal. That's exactly the same as up here, except with these arguments reversed. And you can do the same thing with this sugar syntax. This is probably the one you'll see the most often in production Hoon code. So it's pretty neat. It's you just inner arm, core and arm, right? So like kind of build this, and inside of this context, hold that inner arm. Okay. So, okay. So we just went over two ways that cores can be nested inside of each other. Um, you can compose them to put cores recursively in the right branch in the data branch, or cores can live inside the left branch inside the arms of other cores. Um, and as I mentioned, everything in Hoon is a core. And if you can understand how cores can nest within other cores, you can look at the structure of any large Hoon program and understand what's going on. So understanding this is a really powerful ability. Okay. Any questions on that before we move to the next section? Let me get a little drink of water. You right back. Okay, so if there are no questions on cores nesting inside of other cores, um, let's move on to the next section. So learning how to use cores unlocks some new functionality for us. Um, they let us pull a piece of code and call it, run it whenever we want. Um, if we change the data context for that code, then that's kind of like what we learned before, a function where we change the input and we get a new output, right? That's kind of an important part of programming, that we have a function defined, we have a piece of code defined that we can run with various different inputs and get various different outputs, right? So let's consider the following piece of code, okay? I'll drop it in the chat for you guys. So what are we doing here? We're pinning n to the value 5 to the head of the subject right here. Then we're making a core. That core has a single arm buck, and that arm contains code which evaluates whether n is greater than 10. Okay, so let's set this core as a subject. This is go, and then let's call its buck arm. Oops, I didn't close the core. Let's have that. And then let's call this arm of the core. Sorry. That is going to return a no because the value 5 is not greater than 10. Okay. Um, so let's learn a room that will let us change the value of n before we run this code. Okay. So we want to vary this value of n and then get a new output. Okay. So this send_tis room does exactly that. What does it do? Um, it takes a bunch of arguments. Its first argument is something that you want to change. Okay. Something inside your Hoon code that you want to change part of. Then it takes a bunch of pairs, which is a new address, an address and a new thing that you want to assign it to, and then however many pairs of those that you want. Okay. And then you close it with this tis to close off those indefinitely many children. Okay. So let's use this room to create a new copy of this core, but with a different value for n. Okay, so let's try changing n to a different value to see if we can make it something that's greater than 10 and get a yes. Okay. So let's look at this piece of code. So we're going to call our core, we're going to assign our core to the name GTH10, and then we're going to create our core as before, right here, okay? Then we're going to use this send to Hoon. We're going to say, the thing I want to change is the core GTH10. And then what do I want to change inside of it? I want to change the value n to 11, okay? And then I close it off with this tis room. So if I press enter, I'm going to get is the output of a core, okay? So you can't tell in here, but this is, in fact, this same core, but with n changed to 11 instead of 5, okay? If you want to write that in, oops, sorry. If you want to write that in sugar syntax, which is a bit neater, you can just do like this, okay? GTH10, and then changed n to 11, okay? And that still just outputs this whole core right here. So we can't tell that n changed to 11 yet, but I claim that it is the case, okay? So how do I prove to you that this n changed to 11? Well, let's have the same code, but then set this new core with n change 11 as a subject. And then let's run its buck arm. Let's run its code, which evaluates whether n is greater than 10, okay? And so this is kind of the finale. This proves to you that n was indeed changed to something that is greater than 10, because now when I call this core's buck arm, I get a yes, right? I'm getting a yes here instead of the no as before, okay? Does that make sense to everybody? So again, I'm making it, so I'm setting n to 5. It's head of my subject. I make a core. I'm just going to grab this and put it in its right branch. Okay, that's going to grab that n equals 5, put it on its right-hand side. On its left-hand side, it has a single arm, which evaluates whether n is bigger than 10. Okay, so this is a whole data structure that we created, and we're going to call it GTH10. Then we're going to say, let's take GTH10 and change that structure, change the n inside of it to 11. And then let's run this piece of code inside of it. And then we get this yes, because n was changed to 11 and 11 is bigger than 10. Okay. We can save a step here with a useful syntax trick. And that is, instead of specifying the core GTH10 here, we're going to specify this buck arm of the core, and then we're going to change n to 11. When you do that, it actually just runs the arm for you. So that kind of saves a step there. You don't have to set the new core as a subject again. Okay. So let's see another example of this. Okay. So let's take a look at this piece of code. Here, we're pinning a cell to the head of the subject. That cell has the values a equals 1 and b equals 2. Then we're creating a core. That core has a single arm, which computes whether a is bigger than b. Okay. So as before, this code goes in the left-hand side of the core, and this data goes in the right-hand side. And this pair a equals 1, b equals 2 as is at the head of this right-hand side. Okay. So what can we do? Well, let's call this core GTHAB, define the core, and then use centis to say, let's change A to 5 and B to 3. Well, 5 is bigger than 3, so running this is going to return a yes, okay? And here's the same thing in sugar syntax, okay? So B, here's the core definition. Here we're saying, invoke this buck arm of the core with A changed to 5 and B changed to 3. And then we're going to get a yes, okay? There's a rune we can learn to further simplify our code here, to save another step, to make it look a little bit neater, okay? And that rune is sensig, okay? So sensig takes 3 children. Its first child is an arm of a core. Its second child is a core, and then its third child is a new value to change that core sample, okay? So an arm, a core, a new sample value for that core. And it's going to make that change, it's going to swap that value in, and it's going to run that arm for you. Okay. So we can use this rune to simplify our code. We're defining our core as before. We're going to call it GTHAB. And then we're going to say, let's call this buck arm of this core GTHAB with its values, its sample change to 5 and 3. Okay. And then we're going to get a yes because 5 is bigger than 3. Okay. And the same thing in sugar syntax, just looks a little bit neater. Again, this is all the same. We're making our core, we're calling it GTHAB. And here's the sugar syntax, okay? So we're calling this arm of this core with the new sample values 5 and 3. And that gives us the yes, because 5 is bigger than 3, okay? So that's about bringing us to the end of this lesson. So over the course of this lesson, we've been developing something that looks like a basic reusable function that you can grab and recompute with a custom input, right? We'll make this correspondence even clearer in the next lesson. So again, this is a big and important lesson for your Hoon learning. So congrats on making it here. To recap, we introduced cores as a major concept and studied their behavior comprehensively, including the ways that you can compose them, the ways that you can put them together. We used cores to create basic function-like behavior. In next lesson, we'll demonstrate the power and flexibility of cores by showing all the ways that you can use them, all the different things that they let you do throughout Hoon. Okay. So that brings us to the end. I'm happy to take any questions now or in office hours right after the class. So yeah, thank you.